All right. Let's see. One second. I'm going to make doubly sure that I'm actually live. Yep, it works. Okay, cool. Hey, welcome to the stream. Just redoing my intro because, as always, OBS likes to break things. It's like, oh, hey, we're gonna upgrade this thing and make it cooler and whatnot, and then like I can't stream. So that I think that's what happened last week. If you're here this week, thank you for joining me. And we're going to we're pausing my game dev series, and we're going to resume Essentials of Compilation, which I started, gosh, over a year ago. It's been like 14 months ago, and it's been a huge learning experience for me, both about how to build a compiler, but also about the Gleam language and how to use it well. And on that note today, we need to revisit some of the decisions that we made last year. Because, well, there are bugs, to put it lightly. Where we left off last fall with this series is that we got to the end of chapter 6, and things were working fine on the Erlang target, but they were not on the JavaScript target. And the whole point of the JavaScript target is you can play with this compiler that we're building in the browser. That's really cool, right? Or you could potentially use it from a JavaScript application. Not that you should, but we want that to work so that we can demonstrate the output of all of our efforts. So the problems that we were seeing last fall were oriented around graphs. And graphs are the focus of today's stream. So we're going to fix those problems, I hope. But first, I need to talk a bit about the direction that I've decided to go, and we're going to see if it works. But we're also going to probably have to make some compromises because I have attempted this particular change at least twice. And what I discovered was something about our implementation that we did before caused certain kinds of bugs to be buried, right? And that's not acceptable. So what our goal here is today is to get a graph data structure that we're happy with, that we can use both for the control flow graph, which is used in uncovering live variables. That's in the uncover live phase. And also the interference graph, which is used for doing register allocation via graph coloring. So we need a data structure that will work for both of those. Right now, we have two different ones. The control flow graph, which we'll look at here in a second. Let me just pull it up. The control flow graph is implemented via FFI. So it's an opaque type. It has no constructors, and is parameterized by the vertex type and the edge type. And that wasn't strictly necessary because we only care about the vertices in the control flow graph. We don't care about what kind of edge, like what's the label on the edge. So it's implemented with FFI. In Erlang, that on the Erlang target, that is this little tiny FFI module. And in fact, I realized later I could write these two as just calling digraph directly. But it fakes having this sort of referentially transparent thing that is expected in Gleam by constructing the digraph in the Erlang VM, and they're just like returning, because digraph wraps ets tables, which are mutable, right? So we need to just return the original graph that was returned, and this is like, I think it's just a table ID, honestly, or it's a record or something in Erlang. So this is like really straightforward, and I've used digraph for years. I love it. It's really great, but digraph doesn't work on the JavaScript target. So for JavaScript, we made another FFI. And you can see where this is going. It's like, I wonder what's going to be different. Well, we had to use this Dogre.js graphlib. And it's not, this is not that suspicious. There's nothing really there. But these two likely have different behaviors. So the way to solve this would be to make it all in Gleam, and then it's essentially the same, or at least you can feel confident it's the same on Erlang as it is in JavaScript. So that's one thing that we're going to do today. The other one is the interference graph, and what we did was we took an existing graph library, kind of mucked it up so it could be undirected, and then we and so it could, there's some commented out code in the original source of that library, and we uncommented it and made it work, and it's just, it's a heck of a mess. So I think we need to be, and we also wrapped it kind of unnecessarily, but we need to be better. And so what I want to do is, and I did this on the last stream, the stream that did not get posted, and I want to go through and figure out what functionality we need, right? And then we're going to make a data structure for our own graph that satisfies both of the APIs that we need, or like both of the use cases that we need. I did some attempts, and I want to talk about this. So this is a rant that I wrote last week after my failed stream, and I was upset. I was upset both at the fact that the stream didn't play. It didn't, it didn't upload properly, but also that I was fighting against library authors' design decisions. Now, that's fine. They can build the graph library that they want. But there are two key things here that I wanted to call out that we will try to address with our own. And I really don't want to write our own, but we're in that situation, I think. So there's two flaws with all these libraries, and I'll show you them in a minute. They either require int as the node identifier type. Okay, so let that sink in. Or when you want to put a weight or a value on a node in the graph, it's wrapped in option. And sometimes they do both. I say the first is lazy because they're just using dictionaries. Dictionaries allow you to use any key any type as a key in the dictionary. Why is that? Because there is very well-defined equational semantics on all Gleam types. You cannot create a type which has murky, equality. There are very few basic types, and you build up structures around those basic types, and then all of those inductively have that property, right? Okay, so you could use even a complicated, structured type record of some sort as a key. It doesn't necessarily make sense, but it's possible. And I say the second one is just bad API design because I could say I want my nodes to have optional weights. I can wrap them in option. There's no reason that no decent reason that the library has to decide that for me. Now, if it's in some of these libraries, it looks like, oh, they're trying to grease the wheels at this one particular use case. So they put option in the main type when they could just say, well, these functions only operate over nodes that have optional values, right? Instead they said, well, all nodes have optional values, and if you get an option on a thing, then you need to deal with unwrapping that and rewrapping that yourself. I think it's just bad design. Okay, so I kind of gone over the other things. There are tons of classical graph algorithms that use integers for node identifiers. I get that, but their constraints are different, right? On Gleam, we don't index into collections with integers, or at least we've made it hard. So you're not required to use it as an array index, for example, or as a pointer offset. You don't have to do that. They're not necessarily smaller than other types, so it's not an issue of performance or memory consumption, right? Especially on Erlang, integers have, well, they're big ints. They have unbounded size, essentially. Now, there are sizes that are reasonable and sizes that are not, of course, but it's not that picking an integer is going to give you smaller memory consumption. Not necessarily. Okay, so those are the things I wanted to call out. And what we're going to do is make, I didn't want to do this, but here we are. I'm yelling at the void. All right, just to review, here's the things that I've looked at. Graph. This is the one everybody starts with. It's pretty good. But again, so essentially the graph is a dictionary of integers to contexts. Contexts contain the edges. So it's like an adjacency list type of graph, and a wrapper of a node around the value. The node has the identifier in it as well, so that outside the context of looking at a particular looking at a particular context, you can see what the identifier of the node is. Okay, and it wraps an arbitrary value type. That's good. The problems I ran into with this are when you want to update a node's value, you use this match function. And this match is like a zipper, if you're familiar with that functional programming concept. Basically, it gives you the thing and the context around it. Now, the problem with this is this graph has that context removed from it, which means that if you wanted to go and change the contents of the value type, right, inside this node's context, you have to match, pull the context out. So now I have a graph without that node. That essentially means all of the edges incoming and outgoing from it have been removed from this graph. They're still present in the context, but they've been removed from this graph. There's no function to inject that context back in. Okay, which means that this is only relevant for algorithms where your goal is to remove the thing. Otherwise, and last week I made changes related to this, which it would use match to pull the thing out, we'd update the value, and then we'd iterate through all the edges or so we would insert the node back into the graph, and then we would take all the edges from the old context and add them back to the graph, which is like horrendously inefficient. Useless work, when all we wanted to do was basically apply a function across the value contained in that node. Okay. So, this is the one that we have a version of in our current project where I had changed a bunch of these things. And I don't like it. Okay, the next one, this Aonix graph, in a lot of ways is actually better in that you can specify the key of a node and the value of the node, and of course the label for edges. But it has the problem of the optional value. So rather than this just being value on node, it's wrapped in option. So if you're trying to where is it? If you're trying to, yeah, okay, so it does directly replace the node. So if you wanted to do a modify, you could get the node, unwrap the option inside it, and then reinsert it, overriding this. So I think I want something very different. So that didn't work. Yog, really, like, look at how much stuff this does. Look at all these algorithms that are in here. It almost has, so Yog has, you know, you can pick the graph type, you can add nodes, add edges, and so forth. And then their main thing is like, hey, you can use Dijkstra's algorithm, or you can use Floyd-Warshall, or you know, you can check properties of the graph. That's very useful. But they're not generic. Note that the ID here, so this is add node, ID, and weight, or label. Value, I guess it depends. Okay, so I had a discussion on the Discord with the author, and he says, oh, use this labeled thing. Well, it turns out this labeled thing, this labeled builder, is almost what we want, except that the label is the weight. This is not the key. This is, oh, you have this labeled builder. This is for a degenerate case where the thing you want, the name of the node is same as the value of the node. And that's fine for the CFG, for the control flow graph. It's not fine for the interference graph. We have other stuff in there. So that's not going to work. Okay. And I'm not going to go too deep into this one. I've only looked at it briefly. But again, node ID is an int. You killing me, Smalls. Okay. Enough rant. I do want to point out the digraph in the standard library that we were talking about before, in Erlang standard library, that we're using FFI to call. The types here, vertex is anything. Label is anything. Edge is anything. Term means anything. Any value. So this digraph lets you do whatever you want, which is very useful. Okay, we're going to close all this out. And then, hey, Chris, everything is anything. Yeah. Welcome to the stream. My rant is finally over. Whole 20 minutes into the damn stream. Okay. Okay, so these are the things that we looked at. We're not going to look at anymore. We're going to do our own business. My stream is actually working today. I'm very pleased. I don't know if you run into that, Chris, but like OBS made some changes, and then like things didn't work the way they did before, and who knows what else went wrong last week. Anyway, okay, so we are going to really quickly, we're going to make a little text file, graphs.text, and this is not. No, let's make it a markdown. Okay, so we need. This is basically our to-do list. Software updates. It turns out, yeah, they break stuff. Okay. So we need all the things from the CFG. So let's split right, and then we can see both of these things. Okay, so we need a constructor. New, it just gives us a new graph, right? And there will be some parameter types, right? We don't know what those are yet, but there's going to be a vertex. So we'll need a key, so node key type, and a vertex or weight type. Maybe that's what we call it. I don't think that we use edge types, so we're going to get rid of that. We just care about the node key, let's call it that, and the node weight or value. Okay, so add a vertex or a node. And this is just going to, so we're going to need to change this. This is a case where V is the key of the node. So we need, this is going to take a graph, a key, and a weight. That's what the signature is going to be like, and it's going to return the updated graph. And so this is just like a little bit of, let's not use arrows there because they imply the function. This is going to be like a function of no arguments to return a graph. There we go. Now we're getting more consistent. Okay, we need to add an edge. It's going to take a graph, and it's going to take a to key and a from key and a to key. Since we have no edge values, edge labels, that's all it needs to do. Okay, and then we need, so these are related to how the edges are managed. In neighbors, basically, other graphs call it predecessors. So we'll call it inbound neighbors or predecessors, right? So if the graph is directional, then so we're going to graph and a node key, and what we're going to return is either a list of keys, or we could say it's a set of keys. I think either are fine. We'll have to update our tests if we choose a set over a list. I think the reason why this is a list is because the digraph returns a list here. It doesn't use the set data structure. Okay, and then an outbound neighbors or successors. Out of curiosity, Chris, what do you prefer in terms of the naming on that? Successors, predecessors, or in neighbors, out neighbors? The other reason might be good to use a set here is if we want to get all neighbors, we can internally union those sets. That could be useful. Okay, so that's everything the CFG needs. It's going to be a little bit trickier with the interference graph because this was opaque, right? This type, it has no constructors. It uses FFI to construct it. Yeah, okay. That's a good point. Go with the flow of the surrounding independent code. Yeah. So this one, we don't have to worry about it reaching into the inside, but some of our existing code around the interference graph does a lot of that. And you'll see what we'll do is we'll go and we'll find the places where this is imported, and we'll see where all the mess is. Okay. So, okay, so we need to see, does it have a node? has node, question mark. So this is going to take a graph and a key and return a bool. The other thing that we could potentially do is a get node, and that returns either an option or a result of the maybe we have the key in the caller, so we could say result of the weight or nil. So that's a possibility. And then if you care about has node, you can just match on OK. Okay, so this was like, okay, if the graph doesn't already have this location in it, then, gosh, this is a bool guard situation actually. Then we insert it, right? Okay, and that's fine. Okay, so add conflict, another bool guard situation. Okay, so this is assuming that context thing from Giacomo's graph library, essentially. So it adds an edge. So we have add edge, right? And then we created this modify value function. So we're going to need to like modify in place. And that's going to take a graph and a key and a function from a weight to a weight. And that will return the graph. That's critical function here. And all this is doing is saying in this situation, if this, so we're adding a conflict between two locations in our graph coloring algorithm, our register allocation algorithm, and this is saying if this thing is already assigned, then add that assignment to the saturation set of the other node on this edge, right? That means that it cannot use that particular assignment. That's what that saturation set is about. And it's also it's what's the word for it? It's reflexive here, right? You know, for this one, since you've added that these two are in conflict, if this other one also has an assignment, then you add the saturation set to the other. So they mutually exclude each other's assignment, essentially. That's what this does. Okay, so the has conflict is just has edge. And I think has edge is fine because we're not labeling edges. And this is has a from and a to. And we'll be consistent with above from key and to key. And this should definitely return a bool. I think this get node might be more useful than the has node, but has edge, question mark. Okay, and then this is, yeah, just inserting nodes. Okay. Now, what we need to do is find all the places where we import this and check. So we've already looked at interference graph. Let's look at allocate registers because I think that, okay, the test, no big deal there. We'll address that. So now we need to look for places where it calls graph dot, something in the graph module. Okay. So one of our steps for, we're going to have to talk our way through this, for coloring the graph. So we pick a vertex from the graph, from the interference graph, and then we're using that match thing. So if it matches, so if there is a node with that key, it returns the context for that node, which is the value on that node plus its incoming and outgoing edges, and the graph without that node in it. So here, quickly, let's go to the definition here. We get the context for this node. If we've got it, then we remove the node. What does removed node do? It not only deletes it from the collection, but also removes occurrences of its edges. This is what I was mentioning before. So we may be in for a lot of work here. But I was going to say, I hope it removes the node. Well, yeah, and I think I was mentioning before, it's like a functional zipper in the sense that, but it's like not really traversing the whole collection, just looking at one thing in it. Yeah. So you can see here that's what this is doing. It's say remove the node. Where's this edges variable? Okay. Yeah, I don't. Regardless, I think for this algorithm, this is okay because you've already decided you're going to color this vertex right now. So it's okay to remove this node from the graph. I really don't like it though. Really wish it weren't that way. Okay, and then we pick a color, and then we assign that color to this node. Okay. The interesting thing about this is you look at that, what we're doing in interference graph, and this add conflict, this will never happen, right? Well, no, I take that back. The assignment will happen on registers. So if there's a conflict with a register, this will get called, right? But it's never going to get called here because we're removing it. Okay. So then what I did is I said, so all of the edges on this context. So this is, undirected graph. So the edges are just basically a set. Note here it's a dictionary with just the keys or locations, and the values are null because we didn't have any edge label. Okay, so take the keys, fold over the graph, modify the value in the graph, updating its saturation set. So all of the edges that are associated with this particular location, they get assigned, oh, you can't have this color. So that's part of their saturation set. And you return the value and the remainder of the graph. Okay. So we need to have something, and let's find, first of all, let's find any other calls. So it's just, okay, so pick vertex is calling get me all the nodes. So we need all the nodes. And this is returning, this is the node weights, right? Okay, so give me a graph, and it's going to give me a list of weights. Okay. Because what we want to do is do this filter map and say all the nodes that aren't assigned, give me, okay, so this is why the ID is in there. We could potentially say that this is a key weight, but let's just say list of weight. Okay, so this is saying take the Okay, so going over all of the nodes in the graph, give me a tuple of how big is their saturation set and their ID. And then we want to sort it based on either their set size is larger or their location has a higher precedence. And then we find the maximum of that. So I think, does list max require something to be sorted? Maybe this is just a... Oh, right. We're sorting it so that when it finds the maximum, it picks the first one based on location. Okay, and then it takes the node ID. So this is just pick me the next vertex to color, right? We're filtering out the ones that are already assigned. We're ranking them by their size of their saturation set and their location. And then we're picking the one that has the largest out of that after it's sorted. Okay, so that just gives us a node ID, which is our location. Okay, so those are the only things that we need. I think that this is doable, but in my past 2 attempts at this, what I ran into is I picked a simpler implementation that was pure Gleam, and stuff broke. So, and when I say stuff broke, I mean like the tests reported different results, which has me really concerned. But we're going to try it today. So I want to see if I can do an automated refactor of this. Let me see if that's possible. Kind of call it old graph. Now everything's broken. Let's undo that. Here, rename it to graph. Let's see. Okay. All right. So the essence of these things are pretty straightforward. And I think that what we'll do is we will make we need to make a new module here. Anyone else watching Freerun? Call it graph. And then at some point we'll rename it after we got all these other references. Okay, so we're going to import Gleam dictionary. We're probably going to need Gleam list. And we're probably going to need Gleam result. We'll find out. By the way, I have updated to Gleam 1.16, but thanks to some dependencies, I cannot upgrade standard lib yet. So we are taking a holding pattern on that. Okay, so we need a type, and this is going to take the key and the weight. And I'm just going to say it's a dictionary, and we're going to need another type, possibly. Freezing is great. Yep. It is good. And this is just going to take the node key and the node with the weight type. So we need a node type. And honestly, this doesn't need to be public. So we're saying node takes a weight type. And it's actually going to take the key type as well because we need to represent edges. The other thing that we could do, and I thought about this a lot, there's not really a great way to do it, is we could instead like just have the nodes and then have the edges separately. You know what? Let's try that. Rather than this being anonymous, let's say these are the nodes, and we're not going to care about directionality, except for when we want to so we probably need a directed edge variant and an undirected edge variant, right? Okay, so incoming, we're going to have be a dictionary from the key type, and we're going to need Gleam set because we talked about that. So set type of key. So that's incoming and outgoing. Right, so this looks like one of the other libraries in a large part. We don't have, in our cases, we don't need edge weights or labels. So we don't need to refer to edges by name. Their name is the pair of their two things. I think that if we do the ability to remove a node, we could sorry, I'm thinking here. We could just have it like when we remove node, you remove it from all of the dictionaries. The problem is you also have to go through and remove it as the target edge. Another option might be we could have two variants here. So we can have directed as a variant, which is this, right? All right. Oh my goodness. Thanks for catching up with me, Chris, and I hope your travels are great. So let's just call it directed and undirected. Now, the problem if we do that, I think is actually, we could have a phantom type for that if we need a phantom type. The problem with having different variants is then we have to match on them everywhere, and maybe let's just pretend. And we say if we add a directed edge, it only adds it to the to one or the other collections. Okay. So let's just we're gonna first of all stub out everything here. We need a type. Why did this need? This doesn't need a wrapper type because we decided to put the edges here. We might want a context type, which I'm not decided yet, but which is like a slice of the stuff in here. So we could say that that gives you the context is the weight, incoming is a set of key, and outgoing is a set of key. We might want that. Okay, so we need new. And let's say insert vertex, and I'm gonna grab this as a type to use. So we have a graph, and and we have a key, which is a key, and a weight, which is a weight, and this is going to return a graph. I'll just make that to do. So the insert vertex we could reuse. We probably will reuse as the way to do a modification. The nice thing about the way we structured this is it doesn't have to assume that there anything about the existing edges. We only have to be concerned about that when we remove things. Maybe we should have like that context thing, which is like take a node out of it. We'll see. Okay. Insert edge. We'll make that our undirected one. This is from a key to a key, and this is graph key weight and to do again. We're just going to stub all this stuff out. And this is feeling so much like deja vu because what I did last time is I used Giacomo's graph library. And I built stuff on top of it to satisfy the API that I wanted, and the stuff still didn't work. So that was frustrating. Okay, so when we say neighbors, we said inbound neighbors. You know what? I'm just gonna say in neighbors. We have the graph again, and the vertex is going to be key, and then that's going to return a set of key. And you can see how with the way that we structured this is going to be straightforward to implement those things, because they're just going to be now we could actually do result here. Question is whether I want to put that on the callers of this to know or to make sure that those are actually members of the graph. Okay, we have to do. Okay, so has node, let's do get node instead. And then the has node can be implemented in terms of, maybe we can implement that too. Not a big deal. And this is going to be a result of weight or nil. See how that's really simple to implement as well, hopefully. Okay, get node. We want to do modify. And this is going to take, we're going to take the graph. We're going to take the key, and we'll say width is a function from the weight to the weight, and this is going to return graph. So there's a question about this. I wonder if we need to have directed and undirected variants. I don't think so, because I think if we say insert edge does the same modification to incoming and outgoing, then if you go and you check has edge on an undirected graph, both edges will actually be present in the internal structure. Okay, and let's say nodes. We'll call it node weights. I think that's pretty good. So we get a graph, and that's going to be a list of weight. All right. I suspect there might be other things. Let's look really quickly at our search here and look at the test. Okay, that's not a big deal. And there's some like unnecessary unwrapping here. What we'll do eventually is what we'll do eventually is make it so that we use this as a type alias rather than like with the generics filled in, rather than going and like doing this unwrapping business that is done all over the freaking code. So okay, we haven't used result or list yet. That's fine. Let's go ahead and do our implementation. This is pretty straightforward. We make a new dictionary. The incoming gets a new dictionary, and the outgoing gets a new dictionary. And you know, I could make this opaque. Right now, I don't care. We might want to do some stuff where we like poke in it in our tests, because we're going to write some tests for this booger. Okay, insert a vertex. This should be straightforward. What we will do, we're going to say nodes, insert into graph.nodes. And here, I think I need to change this. Let's change all of this because I'm not consistent here. Let's change vertex to node everywhere. Okay. Then it's not going to get confusing. Okay. So insert, let's see, undirected edge. You know, we could do type safety here with like the empty variants and whatnot, but I'm not going to bother. We're just going to trust that we did the right thing. Okay, so then we'll go graph nodes is nodes. Okay, so that one's pretty straightforward. We just insert the node. Again, if it has the key, then that key is replaced. Okay, so insert an undirected edge. Let's really quickly look at the standard library for dictionary. Upsert. Upsert could be useful. This is kind of similar to what we were wanting for modify. Okay, so what we want to do here is we want to insert so if it actually doesn't matter. This is, we're going to have to insert into the incoming and the outgoing, both directions, right? For both keys. So what we're going to do instead is we're going to say graph insert directed edge, and then we'll just do this one place. From to, and then we're going to say insert directed edge to from. So you were just making it reflexive, right? And now we do the hard part here. It's actually not that hard. Okay, so we're going to say let incoming is dict upsert. So from 2, so this is the incoming for 2, right? Graph.incoming 2, and this takes a function Okay, so this is going to take a function that takes an option of if this thing exists or not. So this is the set of nodes that refer to this. So we're just going to call it inc, and we'll say case inc of some s. Then we're going to say this returns the new value. Okay, so it doesn't require it to be rewrapped in an option. So we're going to say set insert s from. Okay, and actually this is, we can pull this out. Set new. The other thing that we could do here is say inc, and we need to import Gleam option. Okay. We could say option.unwrap lazy unwrap set.new, and then we can say set.insert from. Okay, then we don't have to match on it. What's wrong here? It's just saying variable never used, right? Right, okay. And then we need to update the outgoing as well. And this will be very similar, right? We'll say graph.outgoing. And we're going to update from, right? Because this is outbound from, and we're going to put 2 in there. Okay. And then we say graph, and we update it, the incoming and the outgoing. Okay, so hard part's over. Now for the inbound neighbors, so the predecessors, we have the incoming thing in there. So we can say graph.incoming, and then we will do dictionary get of node, right? And that's going to return result, and we can say result.unwrap or lazy unwrap set new. Okay, so if the thing is not in the, if the node has no incoming neighbors, so like nothing has ever been inserted, then we always return an empty set. And we have the same thing here for out neighbors, except we do outgoing, right? Okay, get node. This is really straightforward. This is dictionary get graph.nodes node. Okay. Okay, so here's where, you know, we have this modify thing. Which is to update the weight of a node in place. So I think this is fine to do a let assert OK here. And then we will do right. So it's very straightforward with this. This is just going to return. I guess the other thing that we could do here is, rather than let assert, yeah, that's fine. I think that we'll find out if this particular thing doesn't work in our code when this starts panicking, right? I think that's reasonable. Okay, has edge. This is really just checking the outgoing set. So graph.outgoing. What am I doing here? I'm getting the outgoing edges from this node. I guess we could do lazy unwrap set new. So if it's not in there, then we just get an empty set. We say set contains 2, right? Straightforward. Again, like, none of this has to be complicated. And yet it was. And maybe I'm being naive. But here we are. Okay. I think we have the entire API that we need here. We're not allowing folding over the graph. We're not really doing any algorithms that require programmatic traversal that we haven't already implemented elsewhere. Okay, so we're going to go back to, let's start with the CFG, because I think it's the most straightforward one. And we're going to find all references to that. Okay, so we need to make some modifications here. So uncover live just said it's, you know, string and there's nil for the edges. So let's go here and we're going to get rid of this parameter. And we're going to say that there's no edge parameter here, right? And so we've got to change that everywhere. Now that doesn't materially change anything about that code. We've just renamed that type. Okay. So now we could say this is a graph, right? And a graph. The key is V and the weight is nil. We don't care about what's in that. We just care about what its name is, right? And in the uncover live, these are names of blocks. Names of blocks in our generated program. Okay. So now we can say graph.new. I don't know if it allows that. Let's get rid of that and see what happens. Okay. Honestly, this is... we can get rid of this module altogether, right? Let's, rather than going this direction, let's go up here and change what we're using here. So we're going to use okay, and then we're going to find all references to, well, we're going to find in this file. This breaks things. So here, what are we doing with the graph here? Okay, so we go into Analyze Data Flow Loop. Okay, so we're going to say graph in... so this list fold could be set fold, right? Set has a fold function. Okay. All right. Where else are we referring to this? Okay, we just call into it again. Here we go, graph out neighbors. Okay, and then we just do set to list. Okay, so this is going to be add vertex is going to be insert node nil, right? Okay. We have a little bit of noise there because, you know, we're not using the value. And this is going to be graph insert edge. And this is directed edge, right? Because on control flow graphs, they're not, they go one direction. The jump goes from one place to another, right? So we insert directed edge. Now I could maybe go and rename this to insert edge and this one to insert undirect, this other one to, oh, they are undirected. Okay, well at least they're qualified there. Never mind. Okay, are there any other things in here that need to change? Okay, we don't need the CFG module anymore. Let's see anywhere else that uses CFG. Nope. Okay. So we're going to delete this file. We're going to delete these two files. And we'll eventually clean that up with Git. It's fine. Okay, Uncover Live no longer uses okay, so let's go look at the tests here, because I think that what we'll discover is that some of this is going to break. So note, we haven't changed the interference graph yet. Nothing broke. This is a good sign. Yay! Because what happened when I changed this last time is that everything all the tests started failing. Okay, so we're going to make a new, just to be consistent here, we're going to make a new test file for our new graph implementation. And let's just make some tests because I want to make sure that when we go and like change all this, that we have the basics covered. Okay, so let's come up with some tests. Empty graph has no nodes. Okay, so we can say let graph equals graph.new, and we're going to say assert error nil. Right, that's a pretty simple one. So graph with one, this needs to be test. Needs to end in test, right? Yep. Okay. One node test. Let graph equals graph.new. Graph. Graph.insert node. We're going to say foo is bar because we're going to mean dumb. Okay, so assert okay bar graph.get node. I don't want to like get this confused with the module name, so we're just going to rename this as G everywhere. Foo. Okay, and we're going to say assert the end neighbors for foo are the empty set. This takes G. And the out neighbors for foo are the empty set. Okay. And we're going to say there's no has edge. This is just like little sanity checks. Foo to Baz. There's nothing there. Okay. All right. With undirected edges. And, you know, again, I feel like we could, let's just put to do there. Run those tests. Okay, so we have the one failure, which is the to do. Okay. Let's set this up. We have a new graph. We're going to insert two nodes. Foo has one in it. I don't know. We're just making this up as we go. Bar has two in it. We're going to insert undirected edge from foo to bar. And then we're going to say assert graph.hasEdge. And these are directed only, so we can say foo points to bar, and we can say bar points to foo. Okay, and I think that let's duplicate that and say with directed edges. And here we'll say it doesn't have this edge, but it does have this edge, right? Okay, pretty straightforward. What other functionality do we need to test? Let's test the modification. Okay. Modification test. Okay, we're going to say let G is graph.new. We're going to insert node. Foo is 1. And then I'm going to say graph.modify foo with a function, and then we'll say I times 100. Okay, and then we're going to say assert OK 100 get node G of foo. That's a pretty simple thing to test. Okay. What else do we have in here? So we have has edge. Let's do node weights. The interesting thing here is that, yeah, let's just grab this. And okay, and then we'll say assert from list 1 2 graph node weights of G, and we'll say set from list. Okay. Okay, so we've tested. Okay, so we have has edge. Let's do. We need to cover the in neighbors and out neighbors. So for undirected edges, the in neighbors and out neighbors are equal. And we need to, oops, we need to duplicate this bit because we want to check bar. And then let's copy this down here for the directed edges because we care about. So if we have an directed edge from foo to bar, then the in neighbors for foo, I'm sorry, the in neighbors for bar are foo. The out neighbors for bar are empty. The in neighbors for foo are empty. Right? And then the out neighbors for foo are bar. So I think that this is better to say, yeah. Run those tests. All right. Those tests are passing. Now comes our next challenge. which is we need to redo the interference graph. And since this had, you know, a new type wrapper around it, I want to turn it into an alias. Okay, now we have no wrapper type, so this is going to break a bunch of stuff. We'll say graph.new, add registers. Okay, so now we have so insert location. Okay, so this is so if it already has it, we don't care, right? If it's error, any error, which is error nil, right? Because that's what getNode returns. Then we want to do this business. Graph insert node. And we're going to do this. This is inserting the key is location. And that's it. And we can unpipeline that. Convert to function call. Okay, that's pretty easy. All right, so fun times. Okay, I did this last week. I'm going to do it again. So we're going to use bool.guard. So when A equals B, return G. And then we do the rest of this function without that case. Okay. And we're going to have to mess with this function because it's a mess. Okay. So we're syntactically correct right now. But the rest of this is broken. Okay, so we are going to, we need to do let assert okay. Rather than a context, a node. And we're going to do the same with B. Okay, and we don't have the context business. So we're going to say, we're going to take our graph, insert node, or insert edge. And this is, for interference graph, it's undirected edges. So we're going to say between A and B, right? Okay. And then we're going to do graph modify A. And here's the weight. This is the node. So what is that value? That's a node, right? So we don't have this context business, so we're going to say case B node assignment. If it's sum I, then it's none, then we return node. The other thing that we could do here, and I think that I tried it in the last stream that didn't upload, is to do something like a pipeline here with map, and yeah, it's not that important. So now we do the same. So we did that one. We do the same modification, but for B. Okay. And then we'll say this is a node assignment. And then we can get rid of the wrapping back up because we don't care. Okay. Just to walk through this and make sure that we looked at this earlier, right? Just to walk through this, make sure that we understand what's going on. So we're checking if A equals B, then there's no conflict to add, so you just return the graph, right? We're not allowing self edges. Okay, and then when there's a conflict between two things, that conflict is always there. There's no reason that it's directed. So we insert a undirected edge. And in fact, this modification of the library from Giacomo, I had removed all the directionality in it. So this is always an undirected graph. Okay, so so we add an edge there, and that edge, it adds the edge in both directions, right? So then we update A. If B is already assigned to a value to a register or stack location, then we insert that into A's saturation set, and the converse. So if B, we modify B. If A is already assigned, then we update the saturation set for B. Okay. Has conflict is just graph.hasEdge. GAB. Okay. Easy enough. Okay. Add registers. We don't need to wrap it in this extra thing. So let's put this, and I feel like I did this last week as well. Okay, so this is taking the registers and their assignments, right? Their colors, and yeah, and we're throwing them in the graph. So we're going to fold over those rather than G is going to be the accumulator here. So pair, and then we'll do this. So location is register, and then we will say graph insert node for G. Let's say let node is this, okay? And that's going to be the key is going to be location, and the node is going to be the node. And then we don't need all this extra business. Okay. I could probably pull this out into a constant. Let's just say const registers, register colors is that. And then we'll, rather than pipelining it, we'll say register colors. Okay. Okay, so we have replaced our entire interference graph with our newly created graph library. But now allocate registers is going to be broken because it relied upon doing stuff with this. So what we're going to do is we're going to hopefully all right, we're gonna fix this. So this is going to be we need to rewrite this. Okay, we're going to say let assert okay, and node is going to be graph.getNode g location, right? Okay, so we're asserting that if we've picked the vertex, then we can get that node out, right? Makes sense. So we can get rid of this. Then we just do node.saturation because that's picking the color. And then we're assigning the color to that node. And then here we're going to say, and we're going to need to look at where this is. Okay, because we don't have the edges when we pulled it out, right? What we have to do then is we'll just say in neighbors for location. Okay, straightforward. So this is just saying, let's do set fold there instead of list fold. The other thing that we need to do is make sure that we insert the updated node. Because if we don't, we're just going to keep coming back to this. Yeah, let's fold over and update their saturation sets, and then we'll insert location value. So that's updating that. You know, you could use modify, but the thing is that we want to get that value out, and we want to return a copy of it too from this function. Okay. Where else? All right, so here we can go, we don't need to unwrap it, it's just a graph, and we go graph.node weights. The thing is, we don't have the, oh no, we do have the identifier in there. So we'll just go, this is just node.assignment, node.saturation, don't need to unwrap the value. That's nicer. Okay, and what other bugs do we have? One right here. What is it? Oh, okay. So where's that? That's just in a test. Okay, interference graph test. Allocate registers. Oh, right. So we no longer have the ID. So I think that what we want to do here, rather than node weights, is do nodes. And this is a place where I don't really like dropping into there, but since our, or wait, hold on. We have node saturation, we can use node location, right? Because that's the key. Okay, that was actually simpler than I thought. I thought I was going to have to go and pull out the nodes and go dict to list, or, you know, so forth. Okay. So now it's just this test that's broken. So we got new, and oops, and this is graph has node, and we're going to say assert we'll do let assert okay underscore equals graph.get node, because we didn't implement has node. We don't need that. Okay. Let's run our tests and see if this even works. It passes! Oh, what a relief. After last weekend, oh my gosh, what a relief. Now that's not to say that everything is correct, right? What we're going to do is we're going to delete this file, and I'm going to make sure that there's no dependencies in here on any libraries that were graphs. The other thing I should do, so that, you know, successfully built that, that's fine. Target JavaScript. Yeah, so obviously there's some problems with integers being too big, right? That's just a warning. Okay, what was wrong with this one now? It has an unused warning? Well, it's not calling explicate control. Okay, I don't know why that is. All right. We're running the thing. Let's open it up. Localhost 1234. Okay, so we have our thing working. Let's just, you know, compile, see what we got. Okay, so it's annotated with the live before sets still. So we, yeah, like this is really simple. Let's get an example out of the book and check how it compiles. And it looks like I need to zoom out so I can see what the heck's going on. Okay, we were in generate prelude and conclusion. Right, so let's get something up here that's an interesting example that does allocations. So we have vector set and so forth. That's intermediate output. All right, we're talking about the arrangement of things in memory. Okay. Here's one we could try. Okay, so it creates a vector of a vector, and then yeah, let's see if that compiles. No, we got an error. What does the console say? Pattern match fail. Let's try a simpler program first. Okay, so let T1 is a vector containing 3 and 7. Let T2 is T1. Let underscore is vector set on T2, index 0, 42, and vector ref of T1. So this is about aliasing, right? Of 0 should return 42, right? Because they refer to the same tuple value. So, okay. We need to debug this, and I think that this will be the last bit that we do today. But we go to allocate registers, and you know, I don't think I've turned on source maps. Yeah. And real quickly, we're going to jump over to the Gleam news. So we got source maps. So let's add that to our gleam.toml. And let's restart. Okay, easy enough. All right, let's go back to that example and see what we get. And we can close that. All right, so we look at this. Yeah, it's still giving me JavaScript. Which I didn't want there. All right, where was the error? Okay, we were in map, translate location. Line 129 of allocate registers. So let's look at that. It should give me correct source maps, but it's not yet. Okay. Where is this called from? I might need to update Lustre DevTools. I recently, yeah, here we go. Okay, so let's see what else we need to do. It's not given us okay, the warning. If we look in build, we should have source maps now. That's interesting. Okay, I wonder if I need updated standard lib in order for that to work. All right. Well, we figured out, regardless, we figured out where the error was, right? So I need to restart. Let's clear. Refresh. Do I still have that map paste buffer? I do. Okay. So let's start with going here. Okay, so it parsed it correctly. It type checked correctly. Shrink did nothing. Uniquify renamed the variables. Explicate control turned it into our C-like language with explicit allocations. Okay, select instructions. Okay, so we've got all of the there. There's no the live before sets. Uncover live has injected the live before sets. Okay, and then allocate registers is the one that fails. So let's go there. So it was in translate instruction. Okay. Let's look again at the actual error. So translate instruction, translate location, and there's this let assert. Line 129. Pattern match fail, no pattern match the value. Okay. So this may be a deeper problem, but we've got in translate location. Okay, if so if we've got a var is basically saying that after we've done all the assignments, let's see where this gets called from. Right, okay. So jump to there, please. Okay, so we take the conflicts, which is a graph. We color the graph and we extract the assignments. Let's go to extract assignments and see what happens there. So we have a list of nodes. Okay, and we have the list of types. Oh, okay. So this is saying if this is a vector, then if it's a variable that contains a vector type, then you want to say it's the root stack. Otherwise, you want to turn it into either a register reference or a dereference on the stack pointer. Right? Okay, that's what that's about. This assigner is actually a function, and I was like getting confused there. Okay, so we're asserting that every node has an assignment, right? So we're folding over a list of the nodes in the graph. And every node has an assignment. And we're inserting okay, so this is just turning our numeric assignment back into yeah, okay. So conflicts is the interference graph, right? Okay, so then we go to the color graph. This is what we were looking at earlier. Oh, and I did this unfold business, which, you know, could have done differently, I guess. Right, so this is pushing okay, I get. This is sort of like take a step. So pick vertex. Should return a location or error nil, right? Okay. So the problem is we're getting down to this bit, and what I'm finding is that this translate instruction is blowing up. So I think that what we need to see is what the assignments are. So if we go up to allocate registers and let's look for this assignments. Yeah, we're going to set a breakpoint. Set a breakpoint here and see what the assignments are. Okay. Let's clear the errors and let's run compile. Okay, so step over that statement. So we have assignments. What is it? Okay, so it's a dictionary with nothing in it. Okay, so let's just let it go. Let's actually not do that. Let's just look at, let's stop here and then we'll step. Okay. Okay, so input is our program. Conflicts is a node, is our graph, right? So it has, our conflict graph has 16 nodes in it. But no edges, right? So I think let's just let it play. And we're going to switch back to Uncover Live because I want to look at I want to look at what's in the Uncover Live. Like if we're getting the wrong stuff, because that's essential for so here's Uncover Live. All right, what? It's actually build interference that I think we care about. So I need to look at that, not. So by the time we get to uncover live, all right, maybe there's just a bug in our pipeline here. Look at the book real quick, because at the end of the chapter there was the flow chart, right? Okay. Here's our flow chart. Moving it over the side here. So, assuming we're going to do the whole stack, right? So all the stuff happened, the type check, etc., happens before. If we get a successful type check, we call shrink, uniqueify, expose allocation, uncover get, remove complex operands, explicate control, select instructions, uncover live. We didn't do build interference. So I think that that's the problem here with our JavaScript bit. We need to still call build interference after uncover live. So let's get there. That's our bug in the JavaScript. It's not anything to do with uncover live comes after build interference. Build interference comes after uncover live. So actually, let's just do that. So we need build interference. So that's why I couldn't allocate any registers. We got all the nodes in there, but no conflicts were recorded. So, and then, yeah. So there as well. After patch instructions, and then there. Okay, so that was our bug. I thought it was an issue with graphs. It actually just had to do with this code. Okay, well, where was our, oops, need to pull up the table of contents here. So 6. All right, let's do this program. And we're going to go to uncover live first. Okay. And now let's try allocate registers, and we should hopefully not crash. Okay, so I still have this. Let's clear all. Nope. Let's just go. Okay, so we don't have any variables left in here. Look at uncover live. We have variable names. If we look at allocate registers, now we have all registers. And stack locations and so forth. Okay, so I think we solved this problem. Let's go ahead and make a commit. Let's first check that it builds, all the tests run, target JavaScript. Okay, it's just complaining about the numbers. I think that we need to look at that. So let's look at that location. Okay, and that's really just, we can't. I was using binary. We could do this with bit shifting. Again, that's just a warning. It's like, oh, hey, if your integer is bigger than 2 to the 52, it can't be represented in JavaScript. But here, so I think that's not going to be a problem. Might be, actually. What does the mask look like? Okay. Yeah, I think we've got this compute tag thing. We need to think about it for the JavaScript target, whether we can represent it properly. The mask allows for 50 elements of a vector. If our vectors are all small, then this is not a problem. We'll never go above that. So I'm loath to take this this warning too seriously, especially since all of our stuff is like working. Yeah, pretty sweet. All right, we've got a lot to do to make our commit. So we deleted all those files. We added that. We're going to trash that file. We don't need it anymore. Okay. Now let's look at the diff for the rest of it. We just added source maps. That's not really doing anything, but we'll stage that anyway. On compile. Okay, so we did build interference. We replaced all of these with graph, right? Okay, so our commit here is going to be replace all graph data structures with our new custom one. Also fixed bug in compiler explorer, accidentally skipped build interference phase, which resulted in no conflicts, and the graph coloring algorithm failed. Okay, so now that that's done, generally speaking, would I recommend doing this sort of thing? No. I think what allowed this to work is that we had very simple needs. We were able to make a data structure that was really simple and covered those needs. And then also, we had, because it was simple, we had a high confidence that it was going to work. And then it was just a matter of discovering all the places that we're using graphs, replacing those places with this implementation, and then fixing the bugs that fell out. And there weren't that many, honestly. I am pleasantly surprised about the attempt this time. It went so much better than my attempt last time. I'm not mad at the graph library. We can easily make changes to this. Is it that efficient? Maybe not. But it's not bad. I think that by focusing on really simple building blocks, we were able to make something that worked really well for us, and that feels good. And I know that if we come upon something later that needs more, we can build upon that. Again, this implementation is not bulletproof. Number one, we allow mixing of directed and undirected. That's something that could be thrown in there as a type discriminant, like a phantom type. We don't we don't check, so we don't allow removing of nodes, right? When you add edges, it doesn't check that those keys exist in the nodes. That's a little safety thing we could add. But this is good enough, and we're not like trying to create something that other people could use in their projects. This is very focused for this project, and that's why I feel mostly okay about it. Anyway, I think this is a good place to stop. Thank you for hanging out if you stuck around. And next week, I think we could probably start Chapter 7. That would be really exciting. So I hope to see you then.